So let me start over again. So what Newton kind of figured out, Newton and Kepler, and we'll talk about Kepler in a second, but a lot in Copernicus, there's a lot of people, and a lot of people since then. But they studied the orbits of like planets and the sun, and they calculated the masses and all that stuff. And what Newton discovered is that there's a universal gravitation between two masses, okay? And the force that's generated, the gravitational force, F sub g, is equal to the gravitational constant g, which, by the way, is this number, 6.67 times 10 to the negative 11 newtons, Newton meter squared, kilogram squared. That never changes. That capital G never changes. By the time you're done with this section, you'll memorize it. But it's the mass of the first object times the mass of the second object all over the distance between them. And r squared is really like the radius, right? If we're studying in two objects that are, one object's orbiting the other or something like that. Okay? Does that make sense? Okay. You guys have that written down?
No.
Yeah? No? You don't have to write it word for word. So like I said before, if I were to turn off Earth's gravity, and I have my reindeer and my elf dude. Well, if we were at the International Space Station, and it had a window, and I could roll the window down and just set these outside, and I just left them next to each other in space, they both have gravitational forces pulling towards each other. And over time, as long as there wasn't any other gravitational force acting on them, they would just drift towards each other. And they would hit each other, and they would do like a elastic, semi-elastic, kind of semi-inelastic collision, and momentum will be conserved, and then gravity will pull them back together, and then eventually they kind of do this. They just stay there. So gravity provides centripetal force that keeps planets and moons and satellites in their orbits, and we can relate this universal gravitational force to the local acceleration due to gravity. So when we talk about G, right, when you compare the mass of something on Earth to the mass of Earth at sea level, G, the acceleration due to gravity, 9.8 meters per second, as an approximation. Truth be told, Newton just took a bunch of stuff and rolled it down an inclined plane. He'd take a ball, he'd calculate what its mass is, find out what its mass is, and roll it down the hill, roll it down the inclined plane. And he would look at it and he would say, okay, how long? He would just do this. He'd just take like an inclined plane, and he'd take a ball that has a mass, and he'd just roll it down the hill. And he would use those kinematic equations, and what he found out is that everything that's in free fall has a constant acceleration of about 9.8, and then he worked backwards from there. Now, another way you could do it is if you remember Newton's second law of motion, that force is equal to mass times acceleration. If this stuff here has a mass, the big M usually refers to the larger mass, so like Earth versus U. U would be little m. That's the force, gravitational force. Well, that's your little mass is being accelerated towards the Earth. Does that make sense? And so we could move that around a little bit. We also have another, if we look at this mathematically, and I divide both sides by m, the little m's cancel, right? Does that make sense? So then what I get is I get this equation that the acceleration due to gravity is the constant g times the mass of the big object and the distance between them squared. Does that make sense? Now that works for Earth, but it works for everything. And so when we look at this, the potential energy is given by a general expression. Gravitational potential energy, if you notice, at some point in time reaches zero. In other words, once we get so far away from Earth, gravity doesn't pull on us enough, right? And that mathematical relationship comes from, if we were to go backwards, like one slide backwards, we said the potential energy, what is potential energy usually? mgh, right? Is that right? And h would kind of be like a value for r. Now, I'm not going to do the algebra, but if we were to do some fancy algebra with this, we'd end up with this equation, negative g mass of 1 times mass of 2 all over r. Now that's important because you're going to do your homework on that. Now the potential energy is inversely proportional to the distance between the two objects. Huh?
Are we doing 3 sections worth of homework?
No. We're doing 3 sections worth of notes today.
Okay.
Okay? Tomorrow we'll do 3 sections worth of homework.
No.
Oh, we'll get it done before you
Be
leave.
gone.
Kepler's law are a result of many years of observation. So Kepler just watched the planets, and it's kind of complicated to calculate, but really you wake up one night and you say, this planet is here, and you wake up the next night and you go, oh, the planet is here, and then the next night you go, the planet is here, and you start to see a pattern, and mathematically you make some calculations, and you notice the orbits. So, and he had very good records, so many years of observation. And they were later found to be consequences of Newton's law. So Kepler's first law is that planets move in elliptical orbits with the sun at focal points. And we call those foci. And so the way that works is, and I got to take this card off here. Let's assume that this card has a mass, right? And let's assume in the middle of the mass, and I won't be able to hold it as much, but let's assume that this is like the sun, and my green cart is like the Earth. So now here's what happens in reality. Pretend that this is here in the center. As the cart moves around the circular path, it wants to go in a straight line, right? But the object that it's orbiting around is kind of moving too. And what happens sometimes is they kind of slingshot after each other. Out in space, what happens is, see how I've got this nice circle? Well, once this cart gets into motion, it kind of pulls that circle. And gravity pulls on the cart, and then gravity pulls on the cart, and the cart comes closer to the object. And then once it gets over here, it kind of pulls on the circle. So gravity has a tendency, and the mass of the object itself, it kind of oscillates like this, right? As this object gets over here, it kind of pulls on that a little bit. And as it gets over here, it kind of pulls on it. Now, it's not that much, but it's not a perfect circle. Well, that's an elliptical path. And Kepler observed this, and they thought they were perfect circles. But what he noticed is it's more of an elliptical path, and there's 2 focal points. The other thing that he found is that these elliptical points, sometimes the object isn't perfectly centered. But it can still have a mass and a gravitational pull. So sometimes an object could be here, way over here, and it wants to travel in the tangential velocity, but the gravity of the sun is pulling it this way. Well, what happens as it gets closer and closer? Well, after some time, it gets a little closer. It still wants to travel in a straight path. The gravitation, now what happens as they get closer? Does the force due to gravity increase or decrease?
Increases.
It increases. So now the force pulling on it is pulling in this direction and it's greater. So what's going to happen to the velocity of this planet? It's going to go faster. But now it's closer. So what happens to the force between the sun and the planet?
Greater.
It's greater and it increases. But now it's closer yet. So now what's the planet doing? Going faster. But it's still closer to the sun, but what's it doing? The force is really strong. Now right here, the force is so strong, but so is the tangential velocity. It's really strong. And it's almost like a slingshot effect. So it almost escapes its orbit right there. But the reason it doesn't escape its orbit is because the force due to gravity is so strong, because the distance between the planet and the sun is so great. The distance is so short. So the force is so great. Well, now it has no other place to travel but this way. And it wants to travel in a straight path. Well, as it starts to get here and it travels in the straight path, the force starts to decrease. It's really strong here and it starts to decrease here because they're getting further and further away. And so you have this kind of elliptical pattern. And so one thing that Kepler noticed is that if you measure the time, the area of the section is equal. So whatever this time is, let's say it's 1 day, the area of this shaded region is the same. This is 1 day. Does that make sense? So equal areas at equal lengths of time.